Alright, so now that you know what the first fundamental theorem of calculus is, and a little bit about why it's important, let's see how to actually use it. This is going to help us solve definite integrals, which solve area under the curve. So there's basically just two steps to it. Excuse me. It says take the antiderivative and then plug in b and subtract the result of plugging in a. B represents your top boundary, a represents your bottom boundary. So we will see in just a second. I think as soon as you see some examples, this will all make sense. So let's start with a very basic one. Let's do the integral from 0 to 5 of 3 dx. The first step is to take the antiderivative. The antiderivative of 3 is 3x. Now I'm not going to write plus c, and I'll explain why in just a minute, but for now just trust me, you don't need plus c. I am, however, going to write a bracket with 0 to 5. Okay, that is just a way to mark our boundaries, because you cannot write your integral anymore. You cannot do that because you've already taken the integral. The integral is the antiderivative part. So once you've done the antiderivative, you should not write the integral sign anymore. So as a way to keep writing the boundary so we know what to plug in, they use that bracket. Or sometimes they'd even just use a straight line at the end with the 5 and the 0 on it. So then you plug in the top number, 3 times 5, minus plug in the bottom number, 3 times 0. And that gives you 15 minus 0, which is 15. So that is the exact area under that curve. Not just an approximation like we had with Riemann sums, it's the exact area. So let's just look at this one visually, since it's pretty simple. Y equals 3 would look something like this. It's a horizontal line. And we'll say that this is 5 right here. So we would be finding the area. In this case, it's just a rectangle. Well, if you think about it, the width would be 5, and the height would be 3. 5 times 3 is 15, which is exactly what we got. So this allows us to find the exact area under a curve. Now I know this one in particular was already easy to find even without an integral because it's a rectangle, but I just wanted to start basic. So now let's move on to a more difficult problem. Let's look at this example, the integral from 1 to 2 of x squared minus 3. First step, like I said, is to take the antiderivative. So the antiderivative of x squared minus 3 would be 1/3 x cubed minus 3x. And then we're going from 1 to 2. So plug in the 2 minus plug in the 1. Okay, so that gives you 2/3 minus 6 minus 1/3 minus 3. And when you solve that, you should get a negative 2/3 as your result. So remember, a negative simply means that you're below the x-axis either entirely or just that most of your, or more of your area is under the x-axis than above the x-axis. So for example, just a really rough sketch of what this looks like, x squared minus 3, something like this. So it's probably from here to here, and we're finding that area right there. But before we move on, I promised I would explain to you why I'm not using plus c. So I'm actually going to back up and look at the previous example and explain that. Okay, so let's look right here. If I had done what I normally do, 3x plus c, here's what would have happened. I would have plugged in 5 for x minus plug in 0 for x. If I simplify that, I would get 15 plus c minus c. And you just get 15 because the c's cancel out. And that would happen every single time because you end up having a c here and subtracting a c here. So the c just disappears. It's not that you couldn't put it there, but it's always going to disappear, so we're not going to bother writing it since it's just going to disappear anyway. So to be clear, when there are boundaries like there are right here, when there are boundaries on the integral, that's called a definite integral, and for those you do not need to write plus c. If it's an indefinite integral, one without boundaries, something that might look more like this, you still need the plus c. So if it has boundaries, if it's a definite integral, no plus c. No boundaries, it needs the plus c. Alright, so now let's keep on and do a few more examples. Let's try the integral from 1 to 4 of 3 square root of x. My first move would be to rewrite that as 3x to the 1/2. You're not required to do that, but I think it's a good idea. Then we take the antiderivative, we add 1 to the exponent and divide by that number. So let's see, add 1 to the exponent makes it 3/2. Dividing by 3/2 is the same as multiplying by 2/3, so we just end up with a 2 out front. 2/3 times 3 is just 2. And we're going from 1 to 4. So plug in 4 minus plug in 1. 4 to the 3/2. Okay, that's the same thing as cubing it and then square rooting it, or square rooting it then cubing it. Doesn't matter which order. 4 cubed is 64. The square root of that is 8. So we get 2 times 8 minus 2 times 1. So that's 16 minus 2, which gives you 14. So the exact area under the curve 3 square root of x from 1 to 4 is 14. We're not estimating, we're getting the exact correct answer. Now you may be asking, well, if this is how we got the exact answer, why did we bother with Riemann sums? The reason is, most of the time in the real world, you don't have an equation. You just have a bunch of data points. So the data points are actually, Riemann sums are actually useful a lot of times for what we have in the real world, because that's all we have is the data points. Okay, let's move on. Let's do one with trig, everybody's favorite. Do the integral from 0 to pi over 4 of secant squared x dx. So you've got to know those trig integrals that we talked about before. The antiderivative of secant squared is tangent. So we get tangent of x from 0 to pi over 4. Now I plug in my b minus plug in my a. Since we all know the unit circle, we know that tangent of pi over 4 is 1. Tangent of 0 is 0. So our answer is 1. So the exact area under secant squared x from 0 to pi over 4 is 1. One key thing to remember is that these are always about area. Integrals find area under the curve. Just like we connected in our brains that derivatives are always about slope or the rate of change, you've got to connect the fact that integrals are about area. So here's an example of one way you may see this question worded. It may say find the area of the region bounded by 2x squared minus 3x plus 2, the x-axis, x equals 0, and 2. Anytime you see area, you need to think integral. So we're gonna set up an integral from 0 to 2, because that's our boundaries. We get that from the x equals 0 and the x equals 2. And our equation is 2x squared minus 3x plus 2. And an integral is always dealing with the x-axis, so we don't have to put anything extra in there. So we just follow the fundamental theorem of calculus. We take the antiderivative. We're going to get 2/3 x cubed minus 3/2 x squared plus 2x. And we're doing that from 0 to 2. Then we plug in the top number minus the bottom number. So we get 2/3 times 2 cubed minus 3/2 times 2 squared plus 2 times 2 minus, then you plug in 0, which if you notice is just going to make this entire thing over here 0. That won't always happen, but it will often happen. So when you solve all that, you should get an answer of 10/3. 10/3. So the area under that curve, the area of that region, is 10/3. Okay, we're going to do 2 more examples and then we'll be done with this. We're going to do the integral from 0 to 1 of the square root of x plus 1 over 2 square root of x. First step is to rewrite the equation. I would rewrite this as x to the 1/2 plus 1/2 x to the negative 1/2. Okay, a word of warning. The 2 right here cannot be brought up unless you make it 2 to the negative 1. And that's just, I don't know, it's the same as 1/2, so why bother? But the x should come up. Square root of x is x to the 1/2. You bring it up top, it's x to the negative 1/2. Our antiderivative gives us this. Plug in the top equation. Top number, top boundary, which is 1. Plug the top into the equation, I think is what I was trying to say, and then plug the bottom one into the equation. If you notice, that's all just going to become 0, so I'm not even worried about that. So I just end up with 2/3 plus 1, which is 5/3. Alright, remember, anytime I'm going too fast, you're welcome to pause the video. I'm going to do one more example. And that's the integral from 2 to 5 of x squared plus 2x minus 3 all over x to the 4th. We don't have a quotient rule for the antiderivative, so we've got to rewrite this first. So split it up into 3 pieces and make every piece divided by x to the 4th. Remember, whenever you're dividing, that you subtract exponents. So this will be rewritten as x to the negative 2 plus 2x to the negative 3 minus 3x to the negative 4 dx. Okay, take the antiderivative, add 1 to the exponent, and divide by that number. And then we're going to plug in 5 and subtract what we get when we plug in 2. So actually, if you're doing this by hand, it's probably easier to rewrite these like this. So then plug in the top, negative 1/5 minus 1 over 5 squared plus 1 over 5 cubed minus, plug in the bottom. If you notice, I'm always putting the second half in parentheses, and that's a good practice because you want to make sure you're subtracting the entire thing and not just one piece. And once you get all that done and figured out, you should get the answer to be 0.0393. So again, that is finding the exact area under that curve from 2 to 5. Okay, hopefully this is helpful. The homework for this section was on page 284, number 5 through 21 odd.